Hello everyone. Today we are going to talk about tissue light interaction. We will see how the light actually interacts with the tissue. We'll talk about the basics, that is we will start from atomistic level, that is we will start about how the light interacts with a single atom, and then we'll talk about diatomic species, and then we go out for more complex tissue. Yeah. So let us understand photons. So the photons is the most fundamental um, particle of light. A photon has many benefits, as what we will see. The first thing that is the benefit is the spatial scale. The photon actually helps us to quantify the properties of the tissue from as small as nanometers, as you can see over here. That could be a cell which has the dimension of nanometers, and as large as our own hand. So we can actually quantify the optical properties of the cell as well as the hand. Um the photon has the property that can help us to quantify in a varied time scale. For example, you can work with a 10 power minus 15 seconds uh, of light source, as well as you can work with a light source which is a very constant light source, like till 10 power 6 seconds. So it has a very varied time scale that you can actually work with. It has multiple functionality. What do I mean by functionality? Means if I shine a light from my mobile phone to my hand, the light will, some of the light will actually permeate through my fingers and will pass over to the other side of my hand. Some of the light will get back scattered, so it interacts with the species or components or constituents in my hand and then reflects back, and some of them it gets absorbed. So all of them could be used to kind of understand the morphological functions within my tissue. It could also be helpful to understand the chemical features. We talk about the spectroscopy today. We'll learn about what is infrared spectroscopy, what is Raman spectroscopy, what is fluorescence spectroscopy, and from these signatures we can actually understand what is the property of the tissue. We can also perform the optical tweezing, that is the movement of a very small particles, because light itself has a very low force to rotate or move a particular object. So small objects in order of micrometer or nanometer size, we can actually squeeze them, we can move it from one place to another place, or we can actually rotate them. So we learn about how those techniques can be achieved. We can also use the we can also quantify the mechanical properties of the tissue. For example, we want to know what is the elasticity of the tissue. We can perform the Doppler laser spectroscopy to understand what is the flow of the velocity of the blood within the arteries or the veins under the skin of the tissue. One of the better or one of the benefit of using light or the photons is that it is compatible. It can be used with other techniques such as MRI. For example, in the MRI, we cannot use any electrical or a conducting material, but to transport the light from one end to another end, we can use a dielectric material, that is silica, for example. So silica is a dielectric material, so it can go inside an MRI. It can be used along with X-ray. It's not going to be any other concern in regards to it, or it being kind of generating its own electrical field like that. So it's kind of multimodal. We can actually build multimodal systems along with optics. Practicability is one of the another very important aspect of optics. But what do I mean by practicability is that it's kind of contactless. So The light source doesn't need to actually get the light source, for example, the laser or the light emitting diode, it doesn't need to get exact contact with the tissue with which it is kind of quantifying the optical properties of. Even the detector doesn't need to be in direct contact with the tissue. So it's kind of a contact-less modality, which significantly is a very significant improvement as compared to other modalities such as ultrasound, which requires physical contact through a gel, so that your impedance mismatch is kind of reduced. One more benefit is that it is actually compact. One of the examples that you have already seen would be a pulse oximeter. It is a very compact tool to quantify the heart rate, for example, or the oxygen saturation pulse rate as well. It is also inexpensive. So the lasers that we use, laser diode that we use are, for example, the red laser diodes, which are operating around 650 nanometers. They cost around 2 to 3,000 at this moment of time in 2023. LEDs, general purpose LEDs are cost like 20-30 rupees for 5 LEDs or so, and specific LEDs, for example, surface mount device LEDs having a very narrow bandwidth are still kind of cost around thousands of rupees, so not much than the ultrasound transducers, which itself cost like in order of tens of thousands. So using multiple light source, multiple detectors is not a big concern. Even the detectors kind of cost around thousands of rupees. So it's not that a costly setup of the system. It doesn't take much money to build an optical setup. So let us go and try to understand what is the property of the photon that we will be dealing with. The first and the most important property that we will be dealing with would be the wavelength. In the case of wavelength, so first of all, let us understand what is a wavelength. The wavelength is the distance between two peaks of the electrical field of a particular light source. Okay. For example, when we talk about the red light source, as I said, the red light source is operating at a wavelength of around 650 nanometers. Now, a red light is nothing but an electromagnetic field. So as you can see over here, it's a sine wave kind of field, which is kind of moving from one place to another place. How fast it is oscillating? It's the frequency. How much time it takes to oscillate from one peak to another peak. It's the time period, and frequency is the inverse of the time period. When we talk about wavelength, wavelength is the distance that the electromagnetic wave travels between the two peaks of the electrical field. Fine. So for different electromagnetic waves, for example, we start with gamma rays. It has a very low wavelength, and as we go on towards X-ray, ultraviolet, visible, which is what we are actually seeing right now, infrared, microwave, and radio waves, which is like 10 power 3 meters. It's like huge. So if you compare it with the actual scales of the natural being, you can see that gamma rays have a wavelength dimension of 10 power minus 12 meters. It's like dimension of a single proton or a neutron, or even smaller quark. Yeah. Now, as you go on towards X-ray, ultraviolet, visible, infrared, and microwave, you can see the dimension of your dimension of the wavelength increases. For example, in the case of visible, we are in the dimension of the protozoa, or it could be an E. coli or a bacteria. And as you go on increasing the wavelength, it could be in the size of the insect when we talk about microwave, then the human being, and then the radio waves. Now the wavelength is inversely proportional to the frequency. So as we go on decreasing the wavelength, your frequency keeps on increasing, as you can see over here. And the relation between your wavelength and frequency is c equal to f lambda, or lambda equal to c by f, and where c is the speed of light. The lambda is the operating wavelength, f is the frequency, and c is the speed of the light. So this is how they are related with each other. In this course, we are going to talk a lot about, when we talk about electromagnetic waves that you see right now, um, we will always talk about wavelength over here. Um, so it's very important to understand the this parameter of the light that we have, that is wavelength. That is how much time, not the time, how much uh, um, spatial distance does it take for two peaks. Okay. So most of the time we actually work with the visible range over here, that is in order of like few hundreds of nanometers, specifically from 400 nanometers to around 700 nanometers. So let us understand like what is actually biomedical optics or light tissue interaction. So it's the interaction between the light and living matter. I would like to show you the demonstration that Professor Bruce Stromberg gave to his class. Um, so what did he do is that he actually flashed a light inside his mouth, and this is what the students actually could see in a dark room. What you can see is that there are few patches of dark regions, and then there are few patches of bright regions. You can also see the eye which is getting illuminated, and there are couple of spots within the skin. So there are a lot of things that you can actually quantify through this image itself. For example, you can quantify what is the absorption scattering. I mean, so you can just estimate what is the absorption scattering, absorption coefficient and scattering coefficient of the tissue from this as well. Okay, so let us go and understand how does the light interact with the tissue from this example of or this demonstration. So let us start with simple. Let us talk about how the light interacts with the matter. That is, we talk about a single atom. So this is how the single atom looks like. It has one proton and one electron, which is kind of rotating in a cloud of around the neutron. Now when a photon actually interacts with this single atom, what happens is that the electron moves from the ground level to a very high energy state within the vibrational level. So we are still within the vibrational levels. So these are all the vibrational levels. And after some time, it actually jumps back to its original position. And while it jumps back, it may not reach to its own ground state, but it may stay a little bit up and down, up and below the energy levels, and it may or may not emit the same wavelength of light source that we incident on this electron. Now this is the case when we talk about a single atomic species. How does the light of the photon interact with a single atomic species? Now let us see if we move from a single atom species to a diatomic species. So this is an example of a diatomic species. There are two neutrons. This is the H2 molecule, and over here now there is not just the vibrational levels that you see over here, but there are now electronic states. Okay, this is the ground electronic state. This is the first excited electronic state. This is second excited electronic state. So there are now electronic states that develop, not just the vibrational levels that we discussed earlier. So now if we shine a single photon, the electron from a ground state of the vibrational level of the ground electronic state moves to the first electronic state, right? And then after some time it could actually come down to its ground state. This is how it actually happens. So this is the case when we talk about diatomic molecule. Now we go ahead and move from diatomic molecule to a more complex molecule, right? So what happens in this? So one of the example of such kind of a molecule is hemoglobin, right? So hemoglobin is the molecule which transports the oxygen from one place to another. That is the most important work of the hemoglobin. But in this polyatomic molecule, what happens is that we just don't have the ground, we don't have the vibration levels and the electronic state, but we also have more states. For example, now we see that we have electronic states, vibrational state, but we also have the rotational state, spin coupling, and translational states as well. But for sake of simplicity, what we will do is that we will choose only electronic and vibrational states to understand how does the light interacts with the tissue. Okay. Now considering only the electronic state and the vibrational states, let us see how does the light interacts with the polyatomic molecule. So this is the polyatomic molecule, that is the hemoglobin. So when we talk about the light, we talk about a photon, and photon having a particular energy. This energy is going to be h cross omega. So h cross omega, cross is the Planck's constant and omega is the frequency. So when I talk about h cross omega, that is the amount of energy of the photon, and that is dependent upon the frequency. H cross is a constant value, right? So we'll talk about more about this at a later stage as well. Okay, so now what happens is that a photon having an energy of h cross omega interacts with the electron. What could happen is that it could just get absorbed within the vibrational level. So if the energy is not that significant, the electron which is at a ground vibrational level can move to a higher vibrational level of the same electronic ground state, and then it can actually lose that energy in the form of vibration. So what it could do some kind of stretching, scissoring, wagging, and there are a lot of other vibrations that can occur to release that energy that it has gained because of the incident photon. Next thing that could happen is if we shine the photon of a particular energy, it could just deviate. It's just like a ball that we are hitting to the wall at a particular angle, and then it will just deviate after hitting. There is no change in velocity after hitting the wall. Okay, so because there is no change in the velocity or change in the frequency in this case, when we talk about photon, in the case of photon, it's always not a velocity which is important. It's kind of important is the frequency, because velocity is always the same. We don't change the velocity, that is the speed of the light, but we change the frequency, that is important. So when that particular photon interacts with a particular polyatomic or diatomic or a single atomic species, the frequency may change or may not change. Now if it is not changing, then it's known as elastic scattering. So few examples of elastic scattering are the Rayleigh scattering and Mie scattering. Now based upon the dimension of the particle or the hemoglobin in this case and the operating wavelength, we may get Rayleigh scattering or Mie scattering. So we will talk about more about this Rayleigh and Mie scattering at a later stage. As of now, I am just giving a brief introduction of how does the light interacts with the tissue. One of the example of the Rayleigh and Mie scattering is why does the sky actually looks blue in color in the daytime, and why in the evening it becomes reddish in color or kind of orange in color. So that is because of the Rayleigh and Mie scattering. Why does the cloud actually looks white in color? Right. So this is all because of dimension of the species within the atmosphere in the clouds, which interacts with the light that is coming from the sun. Now the light or the photon could also interact with the polyatomic species, and after the interaction it could change the frequency. So here the frequency is the frequency is omega, and over here the omega is changed to omega prime. That is always a lower frequency, means most of the time is kind of a lower frequency, but some of the time if you have multiple excitation you can also have a higher frequency. So this scattering where there is a change in frequency is known as inelastic scattering. Few of the example of inelastic scattering are Raman scattering. So you can see an energy diagram of the Raman spectrum, that is Raman scattering, that the electron actually moves from the ground state of ground vibrational level of the ground electronic state toward the higher electronic states and then come back after some time towards the original ground electronic state. And doing that, it actually releases different wavelengths of light source, not the original one. And for a specific chemical, it has a particular spectrum. So each chemical or each composition has its own spectra of how it emits the light source. From that, we can actually distinguish multiple composition, constituents, and others. So this is a case of Raman scattering. Then one more is the fluorescence spectroscopy. That is, the light which moves from the ground state, vibrational state of the electronic state to the higher electronic state, and then comes back through a intermittence step over here. So there is another state. So there is a significant shift in the frequency as compared to the Raman spectra. So in Raman spectra, we still kind of move very close by to the original wavelength that we incident. But in the case of fluorescence spectroscopy or scattering, it's kind of a significant shift in the frequency. For example, we shine the light of red light and we get in infrared. If we shine the light in blue light, we get green light or a red light. It's a significant shift because blue light is around 405 nanometers. That you incident 405 nanometers on the tissue, and then what you get out is around green light, that is 545 nanometers, or a red light that is around 660 nanometers. Right, a significant shift in the frequency. But in reality, of course, it's not just a polyatomic species, but it is amalgamation of many biological substance such as ATP molecules and collagen, lipids, and a lot more, as you can see over here. But as of now, to restrict ourselves, we are going to talk about to a polyatomic species where we talk about only electronic states and vibrational states. Now, another way to understand the energy diagram is using the Jablonski diagram. For example, in the case of fluorescence, the same diagram that you saw earlier could be helpful, can be drawn in the form of Jablonski diagram. So here you can see the same thing, that is the ground state, the electron moving from the ground vibrational state to a higher electronic state, and then there is a non-radiative transition, that is there is no excitation of or emission of light, and then there is a fluorescence which is a radiative transition. Which is kind of significantly lower than the energy level of the absorption. So you actually see a different wavelength of light source, specifically more wavelength of light source or higher wavelength of light source. So we are going to talk more on using the Jablonski diagram instead of the energy band diagram. This is more kind of helpful to understand the transition of electrons from ground to higher and then coming back lower. Okay, so this is how each electronic state, it has its own vibration levels, and then this is the ground electronic state and excited electronic states. Okay, thank you for this session. Next session we talk about how does the how do we quantify the optical properties? What are the parameters to quantify the optical properties, such as absorption coefficient as well as scattering coefficient of the tissue. We will dive deep into understanding what are the different constituents of the tissue, right? So, and what do we need to consider and what not we need to consider. Thank you.